Let's go. Good afternoon, everybody. Thanks for coming out to be entertained by Jose Dincao. He is, as you probably know, a senior research associate here at JILA. He is involved in few body physics in many, many different ways, chemistry and FMO physics and non-equilibrium this and that, some of which he'll talk about today. Jose got his PhD at the University of Sao Paulo in, I can't read my handwriting, is that a 2002 or 2003?
2002.
Two, we'll go with that. After a brief stint at Kansas State, he came here and learned at the feet of the master, Chris Green, and arguably surpassed the master in these areas of endeavor. He is a world-class scientist with collaborations both theoretical and experimental everywhere. He has spent time at the Kavli Institute, the Institute for Nuclear Theory, the University of Innsbruck, and most recently the University of Ulm, where he spends several months out of the year. He does lots and lots of things for the community. For example, he has been chair of the topical group of few body systems of the APS. And in recognition for his work and achievements, he was made a fellow of the American Physical Society in 2015. Join me now, won't you, in welcoming Jose Dincao.
Thanks, John. Very, very nice introduction. Yeah. Is picking up well? A little bit of. How about now? Better? Okay. So yeah, it's always a pleasure to be giving talks at JILA, although I haven't done that much recently. So it's a double pleasure to be here today, right? And what I want to do is take you for a ride, and maybe from there I can try to help you to understand the complex nature of few body interactions, right? And that implies in understanding universality, things that we don't understand in universality, right? Some things that are puzzling us, but also some other future directions that I'm pushing my research. Right? So overall, this is going to take you through a big portion of my research, right? And in a way that I found to tie these things, right, in a story that can keep you entertained, is realizing that what is behind all this, right, is the understanding of the long-range nature of few body interactions, but also the short-range nature, right? What is happening when you have more than two bodies at close distances, right? And I'm doing this following 3 different experiments, right? Each one of them highlight different aspects of the full body problem. The experiments made here at JILA with potassium-39, they highlight the long-range aspect of the body interactions. The lithium-6 experiments in Israel, they already start feeling effects of short-range interactions, right? It's a lot of long-range physics, it's a mix, right? And it's here where lies a lot of the puzzles, right, that we still don't understand, right? And of course, there are a series of experiments here that I'm gonna draw to you. Those are not necessarily related to the long-range physics. That's more related to some form of chemical reactions, right? Oops, that wasn't supposed to happen. So, of course, that's not being done in a vacuum, right? Both in the experiment and the theory side. Well, the experiments probably are in a vacuum, right? But I have been having a great pleasure of work with a lot of other theory groups, right? I'm highlighting here the work with Servaas, Kokkelmans from the Netherlands, that we both have been team up to understand some of the problems of the lithium-6, right? But of course, Paul Julian, Eberhard Tiemann, and Michael Tonza, they are also play important role in different projects in here, right? But the idea is to learn how to build realistic problems, realistic theoretical models out of all this. But let me tell you what exactly I mean, or at least a little bit more precisely what I mean by long-range physics, right? I'm talking about typically large molecular states, right? Like Feshbach molecules, F-mol molecules, and so on, which of course they are also weakly bound. You see that here I'm making sure that I'm saying ultra long range because there are other things that are also long range that are way smaller than these systems, right? But here, essentially, these states, right, they are universal, right? They're extremely weakly bound. Feshbach molecules, we know what they are, right? They appear near Feshbach resonances. In particular, in this case, I'm showing the magnetically tunable one, where when you change the magnetic field, you see a pole in the scatter length, which controls the strength of the interatomic interaction, and then you bind a molecular state. And this molecular state has a universal binding energy, right? It's simply the inverse of the scatter length. So it's a universal state, right? But it's also a quantum halo state, right? Which it differs this molecule from other molecules, not just because they are big, right? Because you can find these molecules, they are larger part of the probability on this molecular state lies in a classical forbidden region. All right, so most of the wave function, depending on the scattering, of course, belongs at long distances. All right, this is a unique molecular state. So what is the mechanism that binds this molecule is different than other kind of molecules. In F-mol states, there are also halo states, but with 3 particles. All right, halo states with 3 particles are more rare, all right? And they originate also from in a regime of strong interactions, all right? In this case, when the scatter length is very large, you grow this attractive 1/r square interaction, all right, that leads to binding between these 3 particles. Okay, and that results in a molecular spectrum, right, that is kind of unique. Right, here I'm drawing the energy spectrum has a function of the inverse of the scatter length. Right, here we see in red is our Feshbach molecule. All right, and for each one of these green lines represent a triatomic molecular state that is formed. As you increase the scatter length, and at exactly the pole, when the binding energy is 0, you have an infinity of these states, right? And that's unique for atomic systems. Atomic systems typically just can support a finite number of states. So this 1/r square attractive interaction is an induced interaction that leads to this kind of weirdness, right? And then, of course, there's various aspects of F-mol states that are counterintuitive. I'm not going to get in detail with all of that. What I want to really is focus on this particular point of the energy spectrum, whereas it's where most of the experiments were able to access F-mol physics. Right? They do that by scanning the scatter length near this point and observing large losses, atomic losses in ultra-cold gases. In this talk, of course, this is the kind of subjects that we're going to be seeing with potassium-39 and lithium. But now going down in this energy spectrum, we go to a place where you now have van der Waals complexes, van der Waals molecules. They are not typical molecules. They are bound by the electronic structure. They're still bound by the 1/r to the 6 interaction between these objects. Right? And you can make van der Waals complexes with very complicated structure, all based on this intermolecular binding. Right? Of course, that I'm not going to be talking about very complicated systems. I'm going to get examples that we can easily access in ultra-cold gases with rubidium-87 and rubidium-85. Right? But we are learning how these complexes are being mated. That's the kind of reactions we are looking. And of course, when you get to the bottom of this, on the deeply bound molecular spectrum, you have the chemistry. All right? This is, the interactions now are dominated by electrostatic. Right? The Coulombic forces are binding this. The electron clouds between the 2 atoms are overlapping at this point. And we are starting some studies here, in particular for rubidium rubidium trimers, and also some other heteronuclear molecules. But this is a new territory, right? This is so I'm going to put this as an outlook of this work. Right. And I just want to highlight now that we have basically 9 orders magnitude in energy, in many orders magnitudes in length, right? And we want to have we want to be able to describe this very different molecular systems with a single model, and we can do that with a single theoretical model. So let me drink some water first. I have electrolytes here that I think are making my mouth even drier. But anyway, so that's more or less how we think these problems, right? That's just the straight out the Schrodinger equation, right? You have the kinetic energy terms, you have pairwise interactions, right? Involve just the pairs of but then you have higher order terms that are non-pairwise interactions. I'm writing just the first part that depends on is a non-additive force involving 3 particles, okay? We sometimes introduce that, other times we don't. And that's not how I do it, right? And the way that we do is the hyperspherical way, right? Which I like in particular. I mean, both ways, whatever way you try to do is going to be complicated. That's the conservation of ugliness, right? But at least on the hyperspherical representation, you can access some physical, you can have a little bit more physical intuition in these highly dimensional systems, right? In our case, we introduce a hyperradius that gives the overall size of the system. And of course, in my Hamiltonian now, I have a hyperradial kinetic energy. I introduce hyperangles, all right? And then I have a hyperangular kinetic energy. And then everything else here becomes the same, okay? The hyperangles is where, if you want to know about the geometry of the system, that's where you're going to do it. You're going to look this more closely. Otherwise, what we do, we solve this problem at fixed hyperradius. So this is similar to Bohr-Oppenheimer. The difference we have to include non-adiabatic corrections, or else this is not going to be accurate. But we get here a set of potentials, just like diatomic potentials, where we now can use our basic intuitions. We just need to read these things differently. Like here is the hyperradius. In each one of these channels, there's 2 classes of channels. One that describe 3-body continuums, 3 free particles, and they are atom-molecule channels. All right, so describe collisions between atoms and molecules. And of course, bound states in these potentials, all right, below the lowest threshold, there are true bound states of this molecular system. Above that, there are resonant states. All right, but then once we have this picture, we can apply all the conceptual ideas of one-dimensional scattering. Right? I think this is pretty unique. Right? They transform this highly dimensional problem into a single picture. Right? Of course, how difficult this problem is going to be is going to depend on the form of your interaction. All right? In the case of universal studies, all right, that allow us to drastically simplify these interactions. Right? And that's, I guess, part of the beauty of the universal phenomena, right, of low energy. Right? When you want to talk about Fischer-By states, F-mod states, you can simplify these states. At least that was the idea. Right? We are getting to a point that we are increasingly including all the details of these interactions to be able to precisely describe what is happening in some of these puzzles. Right? Talking about universality, right? The key concept here, which I think was one of the most impactful developments in the past decade, is the idea that 3-body observables for neutral atoms, the 3-body observables depend only on the van der Waals unit, the van der Waals scales. Right? You can use a very simple interaction model. We call that a single channel because it has just one potential, and you don't need even to include hyperfine interaction. In using this, right, theory was able to predict that every atomic system should present F-MOV resonance when the two-body scatter length it's about 9 times or 10 times the van der Waals length. So it depends only on the van der Waals length of that particular atomic species. Right? That was a very powerful prediction. I mean, it actually was really triggered by the overwhelming experimental evidence. The experimental evidence, we just went after the explanation of why the experiments see, right? Those are the values of A minus, right, which is this resonance parameter. For different atomic species, we have cesium, rubidium, potassium, and lithium, of course, has a function what we call the resonance strength. Each Feshbach resonance can be associated with a resonance strength. When S-res is much larger than 1, we call that as a broad resonance or a strong resonance. And when S-res it is very small, we call that a narrow or a weak resonance. Right? So the Feshbach resonances seems to be very different. They have the strength of them, they are different, but most of the results that for all these different atomic species, they relied within 15% of this universal prediction, right? That was very impressive, right, in the beginning. But of course, that when theory evolved, when theory evolved and we start including effects of the width of the resonance, the theory was actually taken away from what we would expect, right? And that's there's a physical picture why this is happening because there's a repulsion on this three-body system that makes these guys to increase, right? So since then, right, some of these predictions are pretty old. The dependence of the three-body physics on the resonance strength. Since then, we have been puzzling and trying to understand what is happening here. Right? In particular, on this case here, that it looks like that the narrower the resonance is, right, the bigger is the difference, right, between the theory expectation and the observations. And so that makes you wonder if really the width of the resonance actually matters, right, in the first place. And to get there and understand in detail the width of the resonance, the rule of the width of the resonance into these observations, right, we have to construct much more realistic models. Right? So basically, the next few slides is just to tell you what is the kind of physics that we have in a real atomic system. Right? We are at large distances, while the atoms they are dominated by hyperfine interaction. Right? And when so the states are labeled, the atomic states are labeled by hyperfine quantum numbers. When you get short distance, the interactions are, in the case of alkali metals, singlet and triplet interactions. Okay, and of course we know at large distance these guys here are van der Waals forces. In a short distance we have, I've been calling the electronic exchange interaction. That's when the electronic clouds start overlapping. Right? And the electronic exchange, right, is the only force there that is mixing the hyperfine states. Right? So that's going to become an important parameter for us to understand the long-range physics, how the electronic exchange is affecting long-range physics. But unfortunately, I cannot solve these problems, including the full ab initio interaction, just at least for the long-range part. When I want to try to long-range physics, I have to do something because there's just too many molecular states here. All right, so we have to come up with models that can help us do these numerical calculations while still preserving a lot of the physics there. So what we do what we call a reduced atom interaction. All right. We get the ab initio interaction and simply add a repulsive part here that is going to cut off a lot of the deeply bound states in these potentials. Right? But I do that in a very particular way because I want these guys to still preserve, and still give me the right singlet scatter length, the right triplet scatter length. Right? And oh, by the way, if you have any question, just raise your hand and go for it. All right? All right.
I'm actually wondering when will we have three-body interaction?
When do we have?
Yeah, like the three-body interaction.
Mhm.
So I presume that means like it only occurs when the three particles are together. So I wonder where, like, because I know like in nuclear theory, for example, they have that, but I'm not sure for like from, yeah.
So let me put this way.
Can you repeat the question?
Oh, yeah, the question is when we are going to have three-body interactions, right? And what I want to tell you is that this is all three-body interactions. When you solve their Hamiltonian, right, even with pairwise interactions only, you generate, there is a collective three-body interaction. But there is a part of the Hamiltonian that appears also in nuclear physics and appears in chemistry, right? Because that's when the three electron clouds are overlapping, right? That's what we call the three-body force, right? So, but those forces, they are very short range. They start being relevant around 20 Bohr, right?
I cannot write them as a sum of pairs.
Yes.
But it has to be three-body.
Yes. Whatever you do that is not written has a I have to go back to. Yeah. This slide here, oops. It's to show that. You have this interaction term, you break down in pairwise, non-pairwise with 3, then there's non-pairwise with 4, and so on. Okay? Nuclear physics is the same story. But for long-range physics, a lot of the time, a lot of cases, we don't need that term. Because most of the physics happen at such large distance that that part of the Hamiltonian is just negligible. Okay? Where I was? I think I was here. Okay, so we have to truncate the number of bound states by introducing these cutoffs in an interaction, but we also have to truncate the number of spins, the spin channels, just because there are too many of them. All right? So there's a lot of physical insight in going to this, right? Selecting these spins, which ones goes in here and there, but we now believe we have a methodology that is pretty close to reality, all right? And the first case that this new methodology was tested was for the potassium-39 case. The experiment here at JILA was made near this flash bar resonance, I guess 39 Gauss, right? In this hyperfine state, right? 1 minus 1. Right? And this is a resonance of an intermediate strength. Right? When this is actually the JILA data. Right? You see that it has much smaller error bar. So the key here was to really pin down this number accurately. Because a lot of this data here, there's temperature effects that are influencing some of this. So these big error bars, and we want to bring more of a precision, at least on the experimental side, to get very precise measurements. So we have an unambiguous evidence of we are really away from the universal results or not. Right? And clearly, right, the potassium-39 have shown to be the non-universal. So I like to say that the FMOV states of potassium-39 are anomalous. They don't follow the van der Waals universality. They don't fall into this region here. So, of course, there's lots of things that needs to be measured. Right? I think this work showed exactly how to get this measurement straight. Right? And like in here, you can see, for instance, that there are important finite temperature effects that the A minus is just the maximum, the three-body recombination rate, which I'm showing here has a function of the scattering. And depending on the temperature, right, it moves away. But when you get at very low temperatures, it is stabilized there. And that's, so if you don't do a study like that, you are never going to know you accurately your value of this resonance parameter. Right? And also I'm showing here, introducing in this talk, this three-body inelasticity parameter, which measures a decay of the state. Right? That's a connection with short-range physics, right? But it's encapsulated into this single parameter. Oh yeah, just a side comment that this state here, FMO states are typically very large. This one in particular, the size of a virus. All right. Those are updated numerical simulations, right? Updated from our original work here, and we are getting a couple percent from the experimental data with 2 different methodologies, and we are exploring other fastbody resonances, other FMO resonances in potassium-39. This work also explore other manifestations of FMO physics, like interference when the scatter is positive, and you get similar agreement between theory and experiment, and also for atom dimer resonances. Right? There's another way that FMO physics appear in your experiment. And with all this, we were able to say, okay, we understand potassium-39. Right? Potassium-39 is under control. Right? And now, when we start looking to lithium-7, right, which is where everything started falling apart. Right? In part, so my point is that for lithium-7, it is basically giving you a result that is consistent with the universality. Right? But the theoretical prediction is way over here. Right? So there must be some mechanism that is changing this observation, but it's changing in a way to put it right in the right spot. So that's it seems at very most a coincidence, right? And proving coincidences in physics is really hard. Right? If this point was somewhere, anywhere else, I think it would be easier. Right? But it's right there. Right? And that's why we are teaming up and studying not only this resonance, but other resonances here for potassium-39, trying to understand the physics behind these observations. And my point here, that before I keep going, is that lithium is really different from all the alkali species. Right? Lithium-7, it is the one that has the smallest van der Waals length. It has the smallest hyperfine splitting. Right? And van der Waals length is something that it is already related to the length scales of FMO physics. So all this, we are connecting this with a parameter that we are developing. I'm not going to have enough time to discuss this, which is the exchange parameter that measures how important the exchange of the electrons in your system is going to be important for scattering in observations. So lithium-7 it is different, like I said. The observation falls pretty close to the range where you should expect the universal prediction. Right, I'm showing here recombination. There's actually 2 different experiments. There's lithium-7 in 2 different spin states, and the observations, they fall pretty on top of each other. Right? So it's a very strong sign of universality there. Right? And so things seems to be very nice, but when you do the theory, right, that's what you get. Right? You get a resonance way far from what you would expect, you want it to be. That's actually what I would expect based on the pure theory, but the actual problem is over here. Right? So, and that's actually, for a spin basis, that works for potassium-39, rubidium-87, for cesium, works for every other atomic system, but not for lithium. Right? So our idea is to push further with the spin basis, which means including more of the effects of the electronic exchange. And this value now on Servaz calculations, it is going from -30 to -13. That's already the complete basis. Those are highly complicated calculations. There's no, well, there's maybe room for improvement there, but not much more. All right. So there's still something going on there that we don't understand. All right. Our best efforts are moving towards getting close to the experimental observation, but not nearly as close as we succeed for potassium-39, for instance. So I have been pursuing the idea that eventually these calculations are just impractical. This calculation in particular here is just would take forever to reconstruct all this. So in the end of the day, we are going to be able to introduce some parameters for fine tuning and feeding. Like there is a way to do that. I can add a three-body force here, which is going to provide a single parameter that fixes everything. But this is, I can only do that once I really understand what is happening on the system. All right. So the advantage that I like of hyperspherical representation of having potentials there, comes into play in at this moment to understand what is happening to lithium-7. If lithium-7 was really universal, like the A- value falls into the universal prediction, the interaction for lithium-7 should be pretty similar to what you see for rubidium-85 and cesium. But what do we see? First, for potassium-39, the potential that supports the FMOV states, it's already modified from rubidium and cesium, right? And you are already on the intermediate resonance regime. So the potential is shallower, but you still have a repulsive barrier here. This repulsive barrier is the hallmark of universality because it prevents the atoms to really go to the very short range distance. Okay? Now for lithium-7, what we see is this. For lithium-7, this barrier completely disappeared. So before, when this barrier was preventing the atoms to get too close to each other, now they're free to approach each other and then probe all the short-range physics. And more than that, it displays this little bump here. Now the lithium-7 interaction has a potential barrier in on the three-body potentials. And based on this recent experimental data, from the Leb-Skajkovic group, where they measured the binding energy of the FMOV state, they could see that the FMOV state can really exist above the threshold. And it can only do that if there is a barrier there. We have performed numerical calculations to verify all that. There's still puzzles there. But it's starting to allow us to say that FMOV states are anomalous. The interaction is completely different than it is for broad resonances, but it makes it fall into the universal range. So it looks like there is something really coincidental there. June?
Can you explain what does coherent and incoherent data points mean?
That's that experiment where they start with atoms.
Can you repeat the question?
The question is if I can explain what is coherent and incoherent in this data. The incoherent measurements are measurements where they were oscillating the Feshbach field, and stimulating transitions and seeing association of trimers. The coherent one is when they apply a pulse. They have atoms apply a pulse that is tuned for energy that is comparable to the dimer and the trimer. So they create a superposition of an atom, dimer with a trimer, and that display coherent oscillations. There are still lots of things we don't understand on these observations. All right, I mean, it shows coherence for a longer time than the lifetimes. All right, so I think that everything that involves lithium is bipolar. All right, it's complicated. Okay? So, but it's at first light that, yeah, lithium-7 seems to be behaving in a non-universal way. Right. So I now want to try to move you from this long-range physics that involves FMOV states, Feshbach molecules, to something more like van der Waals complexes. Right? And I want to remind you that really, so far, I was exploring, this is the entire landscape of the three-body interactions. All right? It goes up to, I don't know, a few terahertz, tens of terahertz. And what we're talking about is something a much, much smaller scale. Right? And we were using these kind of parameters to understand the universality there. So these experiments now, all right, that I'm going to talk about is a way to access the final states, the final products of three-body recombination. Right? In the hyperspherical representation, three-body recombination starts with 3 free atoms here. They approach to some short distance and do NLS transitions to final states. Right? Typical experiments, they are basically measuring the atom loss. So you don't see atoms anymore, and then you know that they are going to molecular states like this. But it's really not telling where they are going. All right? And that's exactly what we want to look for, how these states here are going to be distributed, the population of these states. And in Johannes' experiments in Ulm, what he does is to let recombination happen in the presence of a laser field that, once it's tuned to a molecular transition, ionizes that molecule. And measure ions is much easier. I mean, to count ions is easier. You can see the signal here by changing your ionization field frequency, and you can see very strong signals of these molecular states. Right? And to do that, right, of course, we have to go deep and understand what is happening here at very short distances. Still, you see, not very short for a chemistry. Right? 50 bar is very large for a chemistry, but it is start getting small for long-range physics. That's more the van der Waals complex length scale. Here is some of the theory and experimental observations. Here I'm showing the body recombination rate has a function of the binding energy. Right? And each dot here, each symbol represents, for the blue ones here represents the molecular states with vibrational quantum number -1, starting from the top. So this is the most vibrationally excited state. But all with L equals 0, 0 angular momentum. And of course, we are shifting this, right, by a factor 10. So all these partial waves here, the different L's, are not going to overlap. We want to show that for each L, each angular momentum up to L equals 10, they all are following this trend, right, which is the inverse of the binding energy. Right? And we are going to states of about 100 gigahertz. Right? In both theory and experiment, I feel like is doing a very good job, considering all the complications that is the real system. Right? One interesting point here is that if I were to put all this data together, you would see that there's no preference on the creation of the angular momentum. I can come with very low energy atoms and come out in a L equals 10 molecular state, roughly with the same probability than a L equals 0. So there is really no selection rule or propensity rule for angular distribution. but it does have for binding energy. So that's a previously unknown propensity rule, right? That the only thing that depends here is going to be the binding energy. And of course, we have done some theoretical models, right, that elucidate a little bit of the process that is going on. It involves sequences of pathways. In the end of the day, we can derive a form for the three-body recombination that has the propensity rule here, and there's also this additional term, right, that encapsulates all the interferences that happens at short distances. Right? And when you start looking to this term, so all these oscillations that you see here, right, around this line, are presumably, within this model, are resulting in some interference effect during the decay. Right? And when you start looking to this interference term, right, and do statistical analysis, what you see is that these guys here follow a Poisson distribution. Right? And that's a sign of the chaotic behavior of the short-range interactions, or what is happening when all three particles are getting together. Right? So of course, chaos in three-body systems and chemical reactions is not a new thing. Right? There has a lot of work done with atom molecule, or I'm not sure how much probably for molecule too. But three-body recombination, that's a first. So three-body recombination, even though it's a very long-range process, it does access this region where the interactions are very complicated. So that was one of the work that we have been doing there. But there's also some other propensity rules that relates to spins. Everything here was without, these cases here, we're not analyzing the spins, but for these cases, we noticed for rubidium-85 that the only molecular states, there are tons of other molecular states in this range of energy here. But they all have a different spin, hyperfine spin state. So they get very strongly suppressed, and they don't fall within the detection range of the experiment. Right? So we were at the same time detecting another propensity rule, is that your molecular state, the molecular states that you're going to populate are only the molecular states that have the same spin state than your atoms. Right? And of course, there are measurements for rubidium-85, and also some of this calculation here shows really the size of the effect. Right? Each number here, 422, it actually means a hyperfine state. 4 is the total hyperfine state of the molecular state, and 2 there means the hyperfine state of the atom. Right? So the red symbols are the ones that have the same spin than your colliding atoms. And all the other colors are different hyperfine spin states. You see that states that have a total F equals 5 and 6, for instance, are strongly suppressed. But states that have the same total F, they're still have a substantial signal, but it's roughly about 20 times smaller than the dominant signal there. Okay? So our idea now is to improve this detection limit, trying to see some of these other molecular states. Now, for other atomic states, of course, based on this, we start expanding our analysis to other alkali species, right? In particular, lithium and potassium-39, and you see that these spin propensity rules start breaking down. Right? Now, for lithium, you can start almost spin states can be created, essentially because molecules for lithium, they're always singlet and triplet. They don't have hyperfine contributions. So, of course, that your atoms are coming in a hyperfine state, and they're going to project out in all singlets and triplets. So there is a breakdown here, and it's also another signature of the importance of the electronic interaction for these atomic cases. Okay. Any questions? It's just an excuse for me to drink water. Okay. So we are now exploring the possibility of control of these reactions. Right? Is experimentally you have to be have much more control than we had so far on these experiments there. And also on the theoretical side, things have to be much better described. Right? We are now exploring two ways to control three-body recombination, define the product state of product state distribution of a recombination. Right? One way is to change your initial state. Right? You're changing your initial state, you see how the product states are going to change. Right? And one obvious way to control your initial state is doing these experiments across a Feshbach resonance. Right? On rubidium-85, away from the Feshbach resonance, we know from previous works that only molecules in the 4-2-2 hyperfine state are formed. At least that's the dominant contribution. But close to a Feshbach resonance, the 155 Gauss Feshbach resonance from rubidium-85, that is mixing with a closed channel molecular state in the 4-3-3 spin state. Right? So across the Feshbach resonance, you're going to have a mix of the 4-2-2 and the 4-3-3 states. And of course, the numerical calculations, I'm not sure if you can see here. I'm just, those are the theoretical calculations for, and I'm highlighting just 3 molecular states here. So this is this is three-body recombination into this 4-2-2 state. I forgot the vibrational and rotational states, but I think that it's going to appear the vibration and rotational quantum numbers of this molecular state. And 2 other molecules with the 4-3-3 state. And as you can see, away from the Feshbach resonance, which is seated right here, the amplitude of recombination to these states is very small, but it becomes increasingly higher and actually surpass the blue line here when it approaches the Feshbach resonance. This peak here is the FMOV resonance that appears in rubidium-85. So the experimental observations, right, really confirms this theory. That here I'm showing the signal for the 4-2-2 state. Now I can see is V-4, L equals 4 dimer. The signal goes, of course, there is this slope is because of the magnetic moment of this molecular state. But you can see that the signal for these 2 other molecular states in this particular spin state start appearing as you approach the Feshbach resonance. And even when you are at Feshbach resonance, you can see these signals very clearly. And as soon you move away from the Feshbach resonance, because on the positive side, there's this strong drop on the signal, and then it's not detectable anymore. So this is one demonstration that, well, we can modify the initial state and see changes on a product state distribution. Now, we are now exploring ways to do that in an optical lattice, right? Where for some particular spin states, you can, just the confinement can change the mixture of your spins. All right? If you make a tighter trap, like a very loose trap, is going to be mostly this spin channel. But as you start squeezing the trap, all these other spin components start becoming important. And that's another way we expect to control which states are going to be formed via recombination. This is more a preliminary results. Right? In this case, we were exploring the idea of controlling the signal, the molecular product state distribution by changing the final state. And as a function, this is rubidium-87. All right, for a given magnetic field, you have 2 dimer states. In this case, L equals 6 dimers. All right, that they avoid the cross. All right, And so near this avoid crossing, you are creating a molecular state that is in a superposition of these two different spin states. And in the theory calculation, that's across this crossing here, it shows this is the signal of three-body recombination before and after and during this crossing. So there's a strong change of the population of these molecular states as a function of the magnetic field. And so far, the experiment have been able to track down this part of this avoid crossing, but for reasons that we still don't understand, the signal completely dies on this side. It might be related to the ionization path they're using, so we are still working on that, right, and trying to understand these kind of things. So this takes me to the final part, right, that those are more recent explorations. I'm start looking to more chemically relevant regimes of binding energy. In the case for rubidium-87, right, those are the three-body potentials that is showing that the red ones without that three-body force that we were asking, right, and the green one is with that non-additive term. So they are extremely important at short distances. Right? But around 20 bar, they start becoming less and less relevant. Okay? But if you really want to track down molecular ground state molecules, in this case, I'm looking to the rubidium quartet state, which has no hyperfine interaction, so it's a simplified case. Right? But the interesting thing of the hyperspherical diabatic representation is that the potentials here, they give you idea of what is happening with the geometry of the system. States that belong to this, it's hard to see under this resolution, but there's a family of potentials that go up, other families that goes down, and this shoulder here, this plateau represents when one of the molecular bindings is broken. Right? So it goes from a triangular configuration to a linear configuration in this regime. So we know which regime we can explore the geometry and so on. So far, we are mostly here my point. One of the motivations of doing that is that this kind of information might be important if you are looking for ways to create these triatomic states. Right? You want to make sure that your target state has a proper geometry than your initial state, so you get good Frank-Coulomb factors. And so far, I'm mostly doing scattering with ground state rubidium triplet molecules, and looking for the density of states, seeing what these peaks here are three-body resonances, and trying to understand the lifetime of these resonances. Some of them are very, very short-lived, but there's some ones here that are pretty long-lived, 100 microseconds. This is one kind of I know there is interest in the field in pushing things towards this kind of systems, to ground state systems. And this is another case that I was looking with ytterbium and lithium. And they have a similar structure. It's a bit different because the diatomic molecular spectrum, they are uneven. The lithium spectrum is much deeper than the ytterbium, but still there's a lot of interest in exploring chemical reactions like this, right, where you are really exchanging atoms. Okay, and of course the geometry of the systems. I'm really interested in looking to the geometry of these systems. So I guess I'm gonna stop here with a long summary that you can skip if you want. But the two major points here, which were things that I didn't have a chance to talk about, of course, it's just too much. But there's a number of things that I've been doing with Michal Tonza, understanding molecular ion formation, lithium barium, lithium ytterbium, via three-body recombination. And also there's a lot of studies that we have been exploring with Cindy in exploring laser-assisted collisions there. Anyway, I just want to thank the people that has been involved in many of the steps that I showed to you. There's Jinglu, which is a postdoc there in Lund that I have been working closely. Tushi is a student here that I share with Leo. All right. This is Steven. He works with Cindy, but he's also doing some of the theory for the laser-assisted collisions with me. Jacek, he's coming here to JILA in the fall with a Fulbright fellowship, and he's doing the molecular ion stuff. So I'm probably gonna get him to give a talk into this, so you can see. And Sean, we are playing around physics. All right. Anyway, thanks everyone. All right.
Fantastic. Do we have questions for Jose? Yes.
So, thank you, Joseph. So my question is, when you have these three-body recombinations, so how long-lived are, is there any way that I can take advantage of these three-body processes or these molecular states and use them for many-body physics? Or, is there, you are measuring mostly losses, yes?
Yeah.
But is there any way that we can stabilize this, or they are just going to cause losses in the experiment?
You wanna cut off those losses?
Is there a possibility, or can I have a system when I create these three-body molecules and trap and they don't collide with an?
Yeah, ultimately, we want to have this level of control. Right? I would like to completely shut down three-body recombination. Mm-hmm. Right? One idea is to use blue detuned light. I have some calculations towards that regime, but that would cut off recombination to all states. All right? And that's good for many-body physics because it's going to make your system more long-lived. But if you are interested in studying the recombination, the chemical process by itself, not the many-body physics, so you do want this process to have a high rate.
Mm-hmm.
So
but if I isolate 3 particles in a lattice, only 3.
Only 3 in a lattice. You still can use blue shielding techniques to prevent losses if you want. All right. Studying at the same time, if you want to look chemistry, like we want to see this process. So we are interested in doing a lattice because we can get much higher densities in a lattice, so the signals are going to be much more pronounced, besides giving us another knob for control. All right. But it depends on what you want. If you want to shut down the losses, well, that's a problem that is out there. All right, and a lot of people are interested into this.
Oh, and now clear across the room.
Run, John, run.
I just want to give you exercise.
Okay.
Next one is you again, right? Yeah.
Jose, I have a question about your propensity. You showed the propensity is proportional to inverse of the binding energy. And I'm actually wondering, since David is here, in chemistry, there is this propensity rule, the chemical reaction rate is proportional to the energy barrier, inversely proportional to it. Is that related, or is that the right intuition even? And then maybe a related clarification question is, why is different L as you go from 0 to 2, 4, they are scaled exactly by 2 orders of magnitude? What is going on with that angular momentum there?
Okay. First, let me answer this scaling here. We did that artificially, by hand.
Oh, that's artificial. So
Yeah.
everything is actually on the same line?
Yes.
Okay, sorry.
All right, so the line is giving you a reference point. Right? It's just that if you put all together, it's going to be too messy.
Okay, understand. It's a display trick. Okay, so then the question only one is why it's 1 over E? Fine.
Why it is 1 over E?
Yeah.
Is this a question for me or for Dave?
I'm just wondering if that's the same intuition that in the.
Yeah, I don't know. I want to hear what Jose has to say.
In our model, this 1 over the binding energy comes out of the long range physics. All right, it comes out of where's the slider? It comes out. I have to be a little bit more technical, right? If I want to explain, it's just that the energy normalization of this scattering state. All right, so there is 1 over the square root of the k vector right here, this state. But you don't need to know anything about what is happening at very short distances. It's just a simple wave function overlap.
I see.
All right, it's very simple actually.
Okay.
All right, but
So are you saying it's like a three-body Wigner law? Or is there more to it than that?
I'm sorry.
I mean, there are Wigner threshold laws for
Yeah.
the hyperspherical
Yeah,
coordinate.
you start with a wave function for 3 free atoms, a scattering state, 3 free atoms, and you know your wave function of your exit channel. Right? It has a lot of kinetic energy. This is 1 over the square root of k in your Bessel function, the energy normalization, and then you just do Fermi-Golden rule, and then you get that. So it's purely long range process.
Okay, hold on.
Yeah, just continuing on this line. This is long. These propensity rules are associated with the long-range physics. And the way I'm thinking about this, I don't have an answer. I have maybe an idea of a place to look, which is a long time ago. If there are analogies in chemistry, this might be a place to look, which is in the 1960s, John Light and Phil Pachukas developed the phase space theory of product state distributions in chemical reactions. So now this is long range, and the idea is a statistical theory which basically says there are a couple things that matter, and in your case, the energy with respect to the binding energy is something that matters. And you've got some spin selection rules, and those matter. And nothing else matters. Everything else is randomized. And then that's your starting point. That's your statistical theory. And then you predict distributions over product states. And if there is an analogy in chemistry, that might be a place to look.
Okay.
Phase space theory of chemical reactions is what you would find it under.
Okay. All right.
And
Thanks.
you want to add to that?
I just might add to that, that what makes phase space theories particularly interesting is when you build in dynamical constraints like conservation of angular momentum and things of that sort.
Spin matters, but other angular momenta don't seem to matter.
Well, this is actually what I was you showed something with, what was it, lithium ytterbium and lithium sort of forming lithium dimer and ytterbium, right?
Uh-huh.
Was that right? And there was, some, your axes, probably were in wave numbers, but you had something like a few hundred wave number sorts of energy differences, right?
Yeah, I guess the units was just Hartree.
Hartrees, okay, micro Hartrees or
Yeah.
micro Hartrees probably, okay. And we've got John here who thinks probably one way, but I've always thought that there'd be interesting propensities for particular resonant populations forming particular rotational states.
Okay.
And I'm sort of wondering, in that particular case where you have a very small amount of energy release and a relatively sparse spectrum of honest-to-goodness, truly bound molecular states, do you see resonances? Do you see resonant effects, or do you see something that looks more statistical in terms of the populations of rotational states? Because this is really addressing this issue: is how important are angular momentum constraints in the formation of chemical products?
Yeah. So far, I haven't seen. Well, first of all, I'm not sure if I have enough statistical data here to do analysis, a relevant analysis, right? But I don't think I can answer that question. Simply as that. I mean, we don't have enough data to see this. All right, but everything that we have been seeing so far is that there's really no selection rules or propensity rules for rotations. Right? And my reasoning is that three-body recombination, in particular, three-body recombination that happens at large distance, a distance comparable to twice the van der Waals length. Right? And those distances, everything is so strongly coupled that it really doesn't make sense talking about partial waves anymore. It just become a really strong correlated system and then flies apart depending mostly on the energy, like which is the energy propensity rule and so on. Now, if you start doing things on the weakly bound spectrum, right, when you get a deeply bound dimer colliding with an atom, they can get to much shorter distances. You're going to start sampling electron exchange, and then it's a different regime. That's a regime that I didn't look to it, but things might change there. Maybe this kind of rotational physics can be a little bit different there.
It's interesting. As you say, you're still
Long distance.
these are still long range, right? And but I'm sort of thinking of worlds where, where molecules, where van der Waals complexes are actually only, let's say, a few Bohr, or 2 or 3 or 4 or 5 Bohr apart.
Yeah.
And in those cases, the evidence is overwhelming for this remarkable funneling into specifically resonant states, even though, this is a dissociative continuum. This is sort of vibrational predissociation.
Is this a general rule or specific in some cases?
Where there are experiments, there's evidence for enormous specificity into specific rotationally paired channels in a continuum.
Okay. Well,
Anyway, it would be
another
fun to talk
interesting
about.
problem to look at.
Yeah.
All right, perhaps if there are other questions, we can bring them down to the front. And let's thank Jose again.
Thanks, Rich.
And more, at some quantity of power, you claim chaos.
Yeah.
What was that quantity?
This has been sort of a thing that John and I, one of the few things that we've disagreed on. Not disagreed.
We've come to blows.
No, we haven't come to blows.